Okay, now that we know what parametric curves are, a way to describe a curve by breaking it down into two functions, one for each coordinate in terms of a parameter, something like time, it's time to do some calculus. So first, it's obviously thinking about slope of the tangent line. So let's recall that tangent line to a curve looks something like this. It's a line which passes through the curve, a point in the curve in the same direction that the curve passes through it. And the direction is, of course, encoded in the number we call slope. When we're talking about the slope of a tangent line, we're always thinking about, well, really slope of any line, you're thinking about rise over run. And when it comes to a tangent line, you're talking about an infinitesimal rise divided by an infinitesimal run. And so your description of the slope is, of course, rise over run as always, but it gets written as dy dx. Now, in order to analyze this for a parametric curve, we're going to have to recall exactly what the definition of the derivative is, because we've got a fundamentally different description of a curve here. And we're going to have to go through the definition of limit definition of the derivative in order to come up with a formula. Okay, so you might recall this formula right here. The derivative of a function h at a point t naught is the limit as a change in t values goes to 0 of the change in the output over the change in the input. That's, of course, the rise over run of a secant line right here. So let's look at a picture right here of this situation. And let's imagine we're after the slope of the tangent line at, say, this point right here. Okay, so that's our tangent line. Let's find it at the point t naught, like our formula there. So it's t naught. And in order to do it, we're going to need this change in output divided by a change in the input. So we're going to need another coordinate, t, which is nearby, up here, say, t. And think about the slope of the tangent line, excuse me, secant line, between those 2 points. We have a right triangle described by those 2 points, which we use to calculate the slope of the secant line. We have over here on the rise, a change in h values, and over here on the run, a change in t values. And so our formula for h prime at that point t naught is going to be the limit as the change in the t values goes to 0. And of course, that's going to be represented by t approaching t naught, right? This t is going to have to be approaching t naught. So we write it as a limit like this, t approaches t naught. And if we look carefully at the description of delta h, then we can see, for instance, that this point right here has the coordinate pair t comma h of t, and this coordinate pair has t naught comma h of t naught. Now, that means that delta h will be the difference in y values, so it'll be h of t minus h of t naught, the difference in y value from here down to here, and the change in the input values, t, will be t minus t naught. And of course, that leads to the substitution right here that gives us our formula. Okay, so we're going to need that together with the quotient rule from Calculus 1 in order to make this derivation. So let's recall that if you want to take the limit of a quotient of 2 functions, well, I don't care what they are, just p and q, 2 functions, then I can calculate it by first doing the limit of the numerator divided by the limit of the denominator, as long as those independent limits exist right here and the denominator's limit is not equal to 0. Okay, now let's think about doing the same description, but for a parametric curve where the change in x and change in y will be described in independent functions of t.